Alright guys, we are starting into our fifth unit today. Fifth of eight actually. We only have this one and three more after it and we're all done ready to start getting into review mode for the AP exam. I can't believe those are already right around the corner. Alright, but for right now we are looking at magnetism. So here's a couple of things that we'll be looking at: magnetic field due to the Earth, some bar magnets. We'll talk about these right-hand rules. So, magnetism. When you hear the word magnet, you probably think of things that you like stick on your refrigerator door. So, it might be a little bit confusing that magnetism is so closely related to the electricity things that we were talking about right before the winter break. Um, and really, there's one force kind of that is responsible for both of these concepts, and that is the electromagnetic force. So one force is responsible for two things that don't even seem like they're related in everyday life. Like, the things you stick on your fridge aren't battery powered. You don't have to plug them into the wall. So how can they even be the same thing? Well, we've seen that there's a relationship between charges and electric fields. So you know that some electric charge is going to fill the space around itself with an electric field. And if it were to be placed in some other electric field, something generated by a different charge, then it would experience a force. So charges create fields and are affected by fields. So we have kind of a similar thing going on with magnetic fields, only this time we're talking about moving charges. That's a really important difference here. So magnetic fields are created by moving charges. And to get that kind of reciprocal relationship here, we would say that moving charges, how can we say this? Moving charges experience a force due to a magnetic field. Maybe a better way to say that would be magnetic fields exert a force on a moving charge. Kind of get rid of that passive voice, I guess. So this little relationship here can kind of help us make sense of one type of magnet called an electromagnet. And these are the ones that you can kind of switch on and off, I guess, kind of at will. So I don't know why this notes packet kind of draws the analogy of cranes at a junkyard. Like, that is something that everyone has some kind of experience with, but I guess we'll roll with it. Um, you know, to move cars around at a junkyard or a scrapyard, they have really, really large cranes that have kind of these big silver plates, and they can, you know, make that a really, really powerful magnet kind of at will, just with the flip of a switch. You start moving some charge around and turn it into a really strong magnet. Another example, which actually might be a little more relevant to you, some gates are able to be locked with electromagnetic locks, and it is darn near impossible to pry one of those babies apart. Really, really powerful magnets. This this relationship that we drew, though, doesn't really explain how permanent magnets work. So those are the ones that, it's just a little hunk of metal that you don't need, you know, to battery power it or have current move through it. It's just a magnet. So that is a permanent magnet. Things that are always magnetic. So like all other materials, permanent magnets are made up of the same kind of atoms. So they still have electrons orbiting a nucleus of protons and neutrons. And like we said just a little bit ago, it's actually this movement of charge that creates these magnetic fields. So in permanent magnets, it actually comes down to the atomic level, the electrons circling around the nucleus. That's the moving charge that generates the field. So in most materials, all the tiny magnetic fields all point in totally random, completely different directions. Point in. So overall, they kind of cancel each other out, right? I mean, a chunk of wood that is made up of atoms, but if you put it up against your refrigerator, it wouldn't stick to it because all those tiny magnetic fields that are generated by those moving electrons are all canceled out. Oh, I thought I was typing. So they all point in random different directions, leaving no overall magnetic field. But it gets a little bit different in materials that are permanent magnets. Then all the tiny magnetic fields, I guess, are oriented in the same direction. So instead of being in different directions and canceling each other out, if they're all in the same direction, they all add up into one big overall magnetic field. So of all create a so we put all the little pieces together and wind up with something at the end. So we could say that when this happens, when all these tiny magnetic fields arrange themselves in the same direction, a material is magnetized. So certain materials, like iron, can be magnetized, and we call these materials that can be magnetized ferromagnetic. So I don't know how many of you are all that into chemistry, but ferro, um, it means iron. So I did not realize how long 2 weeks could be. I feel like I've completely forgotten how to talk about everything. Ay, ay, ay. So ferromagnetic, things that can be magnetized like iron, ferro. We have two other types of magnetic materials. So if you have a non-ferromagnetic material that is attracted by a magnet, we'd call it paramagnetic. So the atoms in a paramagnet line up in the direction of the external field. So you put a paramagnetic material into a magnetic field, and they all line up the same way. They try to match it. Um, the opposite of that, so you have a non-ferromagnetic material repelled by a magnet, that is called diamagnetic. So atoms in a diamagnet line up in the opposite direction. So you put them into a magnetic field or you bring a magnet close to it, it gets repelled because it tries to point the opposite way that the magnetic field is pointing. So little throwback here for when we were in electrostatics. We learned then how to draw electric field lines. We can also represent magnetic fields in kind of the same way. So permanent magnets and electromagnets have a positive and a negative pole. Um, Usually, though, you're probably more used to talking about magnets in terms of the north pole for positive and the south pole for negative. I'm going to throw those in there as well. So north will mean positive, south will mean negative. And really, we're going to be following kind of the same rules that we did when we were in electrostatics. It would be really stupid to have two completely different conventions from then and now. So like when we did electric field lines, magnetic lines are going to go from positive or north toward the negative or the south. So if we had a bar magnet, just a straight piece of some magnetic material, the electric field, let me make sure what color I got here. Red. Okay, we'll deal with red. Alright, so we would go from the north and be attracted over to the south. So this way here. Or like this. Always from north to south. Whoa. Oh. I lost track of where I was going with that one. Uh, let's do one more here, if it'll let me. Yep. Wow, that looks terrible. Let me get that swapped out for something that looks a little bit better. Alright, so here is a little bit neater picture of what it would look like. They curve around from the north end to the south end, from positive to negative. And that was the same convention we had when we did electric fields. You always have the field traveling outward away from a positive charge and in toward a negative charge. Um, if we look at another common type of magnet, the horseshoe shape, oof, here we go again. Alright, so it goes from north directly to the south. Oh my gosh. Wow. Alright, we'll do the same thing. We'll clean this picture up a little. Alright, so here's what it looks like cleaned up some. So we go out from positive into negative. So one more familiar example of a magnet is actually the Earth itself. The Earth is kind of like a really, really big bar magnet. So that first example that we looked at, just the straight line, that's a bar magnet. So really simply, we could kind of use that model to talk about the Earth as well. So the presence of a magnetic field about the Earth, that it kind of generates allows us to use compasses for navigation. Um, and it's also responsible for a few other things. Um, I don't know if anyone has seen or you've probably heard of the northern lights, these auroras. So, why do they happen way up north or way down south? Towards the poles, that's where it's going to be the strongest field. We have also that picture on the front where I kind of did the same thing here. So I don't know how well you can see this picture here, but here's South America, Africa, Europe, North America. So our northern hemisphere is on top and southern hemisphere is on the bottom. So these lines are actually kind of counterintuitive. The way that the Earth acts like a bar magnet, if you look at these arrows, remember they go from the north part of the magnet to the south part. So it's actually flipped upside down. What we call the North Pole is actually the magnetic South Pole, and vice versa. So just a little tidbit to explode your brain there today. But really, the magnetic field for the Earth is a lot more complicated than just treating it like a bar magnet. Um, but that's really kind of the simplest case you could look at it. But we won't deal with really, really complex things like Earth. We'll be looking just at our simple idealized cases. So one charge, constant magnetic field, and that will be for the next video when we move on to the magnetic force on charges and actually calculating it.